Hello, everybody. Welcome to another online seminar presented by Head Acoustics. My name is Jacob, and I will be your host today. Today's session is something that we're calling the New Hats Generation, Application and Use. And as I'm sure you've heard, Head Acoustics has launched a new hats product and an ear, which complies with the update that arrived to ITUT P57/P58. And we wanted to be forthcoming about what that means for you, for your measurements, for your products. And so we wanted to share some measurement data from real world products on the different hats configurations that we can put together with the different ears and ear simulators to see how these differences would play out in practice. So real quick, the agenda for today is as shown. We'll dance from a quick intro on the new hats generation to the exchangeable ears and look at practical measurement data. We'll share info on how we position devices because that is absolutely critical. And then we'll wrap things up and get you guys on your way. First up, let's talk about the new hats generation. So this slide here almost looks like a spot the difference picture. I'm actually presenting two different head and torsos, but they look identical, and ultimately that is the point behind this slide. So what I'm actually showing you is on the left-hand side, the traditional, what we call HMS 2.3 in head acoustics terminology, which is a head and torso with a mouth simulator and ear simulator. And on the right-hand side, we're showing you a picture of the HMS 2.3 low noise with human-like ear canal, which features the new ITUT P57 4.4 ear simulator. And the differences between the two here, maybe you look closely on the shoulder and you can see that we have engraved the one on the right-hand side with low noise on it, but otherwise they are completely the same. And I think that's the point, because when you are looking at a head and torso simulator from Head Acoustics, they are all going to be the same shell and the same physical dimensions and have the same acoustic interaction with the sound field. However, I think where things get a little bit more interesting is if we go inside of the head and torso. And you can see on the left-hand side, we've presented a cutout of what the ear and ear simulator sort of looks like in the traditional, what we would call the 3.3 ear. So it's a cylindrical ear canal terminated by a two-branch coupler. The coupler itself is standardized in IEC 6318-4. And on the right-hand side, there is a similar cutout of what the 4.4 pinnae looks like. And so immediately off the bat, you should be able to see that there have been changes to, very slight changes to the pinnae, but primarily in the concha and ear canal region, which has now been designed to be anthropometric or anthropomorphic, basically meaning human-like. And it is terminated similarly by a two-branch coupler, but even that coupler is going to be different than the one that's used in the 3.3 configuration, so slightly different transfer impedance and the like. The bottom line is, with the new hats generation, not only have we seen evolutions in the mechanical design aspect, making the head and torso is more alike and more consistent and more robust and so on and so forth, we've also changed the way that we now mount the microphone to equalize the mouth. So we want to place a microphone at the MRP, and that is done using that little tracheotomy hole in the throat, and a little mounting fixture makes it super easy. And of course, worth noting here is that all of the head and torsos in our product portfolio comes standard with full band mouth performance. Additionally, we made some changes to the top mounting area and of course the modular and swappable ears. And speaking of ears, let's take a quick look at what this new framework allows us to do. If we look at this like a tree, the first branch shows the traditional cylindrical straight ear canal with the IEC 6318-4 coupler and the 3.3 pinnae. We can also offer it with a 3.4 simplified pinnae, but As we go down the tree here and we look at the different branches, you can see that we also offer it in a low noise version, same type of ear canal design, the 3.3 pinnae. Now, of course, the reason why we offer this are for those unique instances where you're looking for a very low noise floor, below the threshold of human hearing. Those are, ANC type application, other electronic product noise applications where you're interested in measuring every small detail. And we can do that using the low noise coupler. And then I think the most interesting one in today's slide deck is going to be the 4.4 pinnae and the associated coupler that goes with it. So you can see the coupler location. We also saw that on the previous slide, sort of a slanted design. It's only going to be mated with that 4.4 pinnae, which, by the way, comes in two different variations, two different color schemes. The bottom line is this constellation and this configuration is going to give us the most accurate representation of a human ear according to the ITU-T P57 standards. It stands to reason that if the concha is more realistic, the ear canal is more realistic, we still have a realistic pinnae itself. And we've made some changes to the ear simulator on the inside, then we should have the most realistic representation of the human ear. The big question, of course, that we'll uncover a little bit later is what does it actually mean from a product test standpoint and product performance standpoint? Now, I talked about these swappable ears. Maybe you get a sense of what it's going to look like. I can actually show you exactly what it's going to look like using this brief video here. So, as in years past, if you're familiar with the Head Acoustics product line for head and torsos, we have 3 little hex screws that we use to attach the pinnae to the head. Once you remove the pinnae, we have 3 additional screws that fix the coupler to the egg, the shell of the head and torso. Once those screws have been removed, you can now remove the ear simulator, and then if you look closely inside, we are using a very short LEMO cable to attach it to the connectors inside of the head. Now, if you've used LEMO connectors before, you're aware that there's a sleeve on it that retracts the hooks in the connector. What we've done is we've installed a little metal loop onto that so that even people without very dainty fingers can go in and grab the connector and release it. And it's as simple as that. And of course, putting in a new ear canal, you do the same thing in reverse. Insert the LEMO connector and then insert the ear simulator, screw it in, and then put the pinnae back on again. It's as simple as that. And that's one of the core features with the Head Acoustics products. Now, speaking of, just wanted to give you a quick overview of the different variants before we dive into the actual measurements. But the HMS 2.3, that is the all-purpose workhorse of all telecom measurements. This is the one that's been standardized for a long time, uses the traditional 3.3 pinnae and ear simulator, cylindrical ear canal. I think we're all familiar with that. And then we have a few variations to that. The low noise version, same cylindrical ear canal, but a different impedance converter with a different microphone. And then we have the HMS 2.3 low noise HEC, which is the human-like ear canal. That uses the 4.4 pinnae. And then we also have the different versions, the HMS 2.4, which is a head and torso without a mouth, so used for listening only applications, so purely headphone applications, some in-car communication situations where you only want to get the listening perspective. We also have the 2.5, which is the talker only, so it comes with the pinnae, just doesn't have any ear simulators in it. But it certainly has a mouth, and it can be used for all talking, speaking applications. Again, like ICC, acting as the driver in a car, in-car communication, or speech recognition testing scenarios. And then the HMS 2.6 and the sister variant, the HMS 2.7, those are head and torsos with microphones at close to the ear entry point, meaning there's no ear canal to speak of. There is no acoustic impedance simulating the inner ear of a human being, and these can really only be used for far field applications, basically where the product doesn't come on or near or in the ear. And the cool thing about the HMS 2.7 is we have them with ICP mics, so you can connect them straight up to handheld recorder like the Squadriga portfolio in the head acoustics world. So with that being said, let's take a look at our mobile phone measurements. So we went shopping and we purchased 3 recently released mobile phones, all relatively high end. And we took 3 HMS 2.3 versions, the traditional 3.3, the 3.3 with the low noise, and then the new 4.4 version. And what we wanted to look at was specifically, do these head and torsos have any influence on the frequency response? And if so, is this something that's going to show up in something like polka measurements, where we measure the speech quality? And then also, is there any correlation with the amount of listening effort required in noisy environments? And we use pink noise, but also inside bus and train station noise. So the idea is just to see, does the pinnae, does the ear simulator affect how we do measurements with, in this case, mobile phones? And very briefly, looking at frequency response, our 3 mobile phones, well, first of all, device A, it was only wideband capable, whereas device B and C were super wideband capable. So we measured those in super wideband mode. But when you scan across the 3 different products on the 3 different head and torsos, so just to be clear, the color scheme that we'll be using today is the blue or cyan color, is the traditional 3.3, the one that's been standardized and used for a very long time. The purple or magenta color is the 3.3 low noise version, so same exact pinnae and ear canal, just a slightly different impedance converter or ear simulator on the inside. And then finally, in green is the HMS 2.3 with a 4.4 pinnae. And looking across, there are slight differences, but really nothing to be super concerned about. And those differences primarily show up because of the small changes to the ear and the concha shape, and the ear canal for that matter. Because if you look at the blue and the purple curves, those are nearly identical. And that tells us that the majority of the changes that we're seeing here aren't related to the ear simulator and the potential changes in impedances that we have in there. Rather, it's more of a physical mating the product to the ear and how that sound travels into the ear and reaches the eardrum. However, the differences are still very, very slight. Now, when we take a look at polka, I think no surprise, if you look across the board, device A performs equally well on all 3 ear configurations. Likewise for device B and device C. When we look at listening effort, so now, of course, we're blasting noise out of the 3-pass system. The differences that we see here, frankly, we attribute to statistical fluctuations. There's really nothing here that stands out one way or the other with any confidence to say that there's a difference in measurements if you are testing mobile phones. So what I want to reiterate here is that the traditional HMS 2.3, the workhorse for telecommunication measurements, this is the standardized version for mobile phone measurements in 3GPP and ETSI and so on and so forth. This is what we can continue using. And if for some reason you need to use a 4.4 version for in-ear testing or other applications, we'll talk about that in a minute, I think you can have a lot of confidence in the fact that you can use the 4.4 head or ear for mobile phone measurements and get very, very close to exactly the same results as you would with a standardized 3.3 ear. So I think that's the key point to remember here. Now, speaking of other types of measurements, let's switch gears and look at headset measurements. So for headsets, we had to grab a couple more products because, of course, headsets, well, there are a few more types. So we grabbed 2 different circumoral headsets. Circumoral, sometimes known as over the ear, are the ones that are depicted there in the leftmost picture. Then we took 2 supraoral, and the supraorals are the ones that are also known as on the ear products. That's the middle image. And then we took 2 in-ears, And the in-ears, of course, they sit inside the concha, maybe even inside the ear canal. And this, as you can imagine, is where we'll see the most variation. When we took these 6 products, we again used the same 3 HMS 2.3 versions, and we looked at frequency response, listening effort, and then also looked at passive insertion loss and active insertion loss spectrally to see if there's anything that we could discern in terms of fit and seal and position of the products on or in the different ears. So here, first of all, we're showing all of the receive frequency responses. And because we're now dealing with headphones and audio products, we're also dealing with binaural signals. And so we're using the same color scheme as before, but now we have solid lines representing the measurements from the left ear and the dashed or dotted lines representing the right ear. Left-hand side, those are the 2 circumoral products. Middle column, those are the 2 supraoral products. And on the right-hand side, we have the 2 in-ear products. And generally speaking, what we're looking for here is obviously comparisons of the frequency responses from each of the products on each of the 3 head or ears. And then likewise, we're looking for symmetry in terms of left-right channel matching. And that's especially true for the in-ears, because that's where the shape of the concha and the ear canal really comes into play. Now, this is a lot of data. It's hard to really discern much from such a high-level view. Let's take a look and a close-up at some of the individual products. So the first one we wanted to look at was the circumoral product number 2. That's an open-backed headphone, passive analog headphone. There's no DSP in it. And when we look at the overall frequency response of the 2, generally speaking, there's not a whole lot of difference with how these responses line up. Of course, there's some kind of a major difference right around 5 to 8K. And then again, there's some variations relative to the other versions, the 3.3 and the 3.3 low noise at higher frequencies, so 12K and above maybe. Most of those differences we attribute to geometry and impedance. If you look at the curves for 3.3 and 3.3 low noise, you can see that they're very similar, and both of those ears have the same pinna and ear canal shape and the same impedance, namely the one from IEC 6318-4. In the case of the 4.4 ear, both the pinna and the ear canal have slightly different geometries, and the impedance is also different as we follow ITU-T P57 here. Generally speaking, there is some difference in results for circumoral headsets, and to find out which one has a bigger impact, geometry or impedance, would require a much more in-depth investigation. Now, if we go look at the in-ear products, first we'll start with in-ear product number 1. Before we even look at the measurement, we should just let it be known that physically measuring these products can be a little bit tricky, because frankly, the only way to really mount them and get them to sit in the ear is to push them very far or deep into the ear canal, very tight into the ear canal to get them to stick. Now, I'm sure if you've measured earbuds that go into the ear canal, even the slightest bit, you've had similar experiences. It can be very, very difficult. And I think our experience with this, likewise, was that it's a very unnatural fit that we end up with. However, for better or for worse, it's relatively consistent. You just jam it in there and it sticks, but there's not a whole lot of variation in how we can do that. Nonetheless, when we look at the frequency response measurements, with that in mind, we see that for the 3.3 and the 3.3 low noise that have the same ear canal, we end up with more or less identical insertion depths and position. And the 4.4, you can see there's definitely a difference. And with the insertion depth in particular, we can see when we look at the resonances at somewhere around 7K, 11K, and maybe out at 15K, there are some clear differences in where those resonances occur. And the primary factor for that is the insertion depth, right? If we insert the product deeper into the ear canal. We shorten the distance between the acoustic center of the driver of the product and the eardrum. And so we're talking about higher frequencies where the wavelengths of the frequencies would cause standing waves and other resonances to occur. And so if we think about how the product behaves on a human being, how it fits and seals and performs on a human being, we would argue that the 4.4 is just a more natural and easier way to do it. And another thing we would look at, of course, is that channel matching. And in general, we really like the way that the 4.4 allows us to position the in-ear product on the head versus what we have to do, we are forced to do with the 3.3. Now, if we look at the other in-ear product, the physical dimensions of product number 2, in-ear product number 2, was a little different from in-ear product number 1. So we didn't have to go to the same extremes about inserting it into the ear canal. And therefore, the frequency shift that we see at 6, 7K, 10K, and so on, isn't as severe between HMS 2.3, 3.3 and the HMS 2.3 with the 4.4. But once again, especially sub 1500 hertz, you can see the differences in the insertion show up between left and right channel when we look at the blue and the purple colors, whereas with the green color with the 4.4, we are able to position these very precisely and closely related between left and right, so we get good channel matching. That's the goal. Now, let's take a quick look at the listening effort. So in this case, what we're doing is we're playing speech out of the product, measuring it at the ear, but at the same time, of course, we have our 3 different noise scenarios: pink noise, inside bus, and train station. And if you look down across the columns at first glance, it seems that these differences are pretty much close to random. C1 maybe, so circumoral 1 maybe benefits from the 4.4 pinnae, where supraoral 1 maybe benefits from the 3.3 pinnae. The differences in any case are small, and maybe that has more to do simply with that particular product and the interaction with the ear in question. However, at least in general, the in-ear headsets, both of them, 1 and 2, despite their different physical shapes, seem to benefit a little bit from the 4.4, although again, the difference is small. So I think it gives us a lot of confidence that the measurements here are going to be consistent when it comes to listening effort in the presence of background noise. Now, related to that was we wanted to look at the passive and active insertion loss, and we take a look at the passive insertion loss first. Again, same color scheme, and we look across and we see, maybe not surprisingly, the supraoral headsets give the worst passive insertion loss. They don't block the ear canal particularly well. Circumorals, a little bit better, and the in-ears, they do a decent job of sealing out the ear canal and give us better attenuation the lower we go in frequency. But once again, let's take a quick look at some of these products. The supraoral, product number 2, doesn't have a whole lot of padding on it, and maybe as a result, it doesn't really show much difference regardless of which pinna, which head you're using or which hats you're using. There isn't really a whole lot to uncover with this product. If we then go look at the in-ear product number 1, we see that the main benefit here is in the form of channel matching, right? So the left-right difference here is absolutely minimized when you look at the green curves versus what you see with the blue or the purple curves. And that's, again, just a product of us being able to fit and position the devices more naturally, which I think is reasonable to expect. If you look at the standard, look at the way the product is, the ear product and the ear canal and the concha is designed. Again, this product here is incredibly difficult to actually position in the ear canal. And there's no real wiggle room in terms of adjusting for left or right. It's really, you jam it into the ear canal and either it sticks or it doesn't. And that's about as far as we can go. And that sort of shows up here when we're measuring the passive insertion loss. For in-ear product number 2, I'd say the same thing. The channel matching is better here. And because it sits, generally speaking, better in the 3.3 pinnae than in-ear product number 1, the problems that we saw with that one isn't quite as bad. But my preference here is still towards the 4.4 pinnae on the head and torso. Now, if we switch and just looked at the active insertion loss, for the active insertion loss, there's really only 3 of our products that had ANC, the 2 in-ear products, and then Circumoral number 1, which is a closed back headphone. And again, what we're looking for here isn't really how good the ANC is. More so, we're looking at channel matching, and if we can get the left and the right channel to perform identically, to get the product to sit and fit better on the ear and in the ear. And all this talk about positioning and how crucial it is, we wanted to give you a closer look at how we position the devices. Now, obviously for the mobile phones, we're using our automated handset positioner, which gives us a rock solid placement and replacement fit of that mobile phone. Once you have it dialed in that little cradle in the hand, the positioner will bring it up to the ear at exactly the same location every single time and gives us a rock solid positioning. Unfortunately, we don't yet have that feature and functionality available for headphones and in-ear products, so we have to go about it a little bit more manually. And the way that we do that is we use Aqua, and specifically in Aqualizer, we have the play and record feature with an online analysis option, which allows us to play any type of noise or stimulus into the product, and then look at the live frequency response of the left and the right channel. And then as we fiddle around with the product live, you can see how the performance and basically the output of the product changes as we measure it in the ear of the head and torso. And with the play and record feature, it's pretty simple. We typically advise that you use program noise or white noise, something that stimulates the whole frequency range if your product allows for it, because some products might reject something as simplistic as white noise. But it's a good stimulus, but you can drop in any other noise source or stimuli that you want. We choose the output channels, which would be the headphones, and then we measure on the input side, so the left and the right ear. And then we look at this frequency response here in our online FFT. And specifically what we like to do here in the online FFT option is we like to choose an FFT size that's relatively small, so like 2K. And then we do a very high amount of averages, 10 averages, 7 to 10 averages, and we enable smoothing, because otherwise, without all those averages and smoothing, you're just looking at a whole bunch of bins, frequency bins that are hard to really nail down. But doing that, we like to change the traces to make the traces nice and big and enabling the drawing of mixed colors, so you can see that third color show up when you have total overlap. That makes it so much easier. And just to point out, that video was a simplification of the process, because mounting in-ears in particular can be a little bit of an art form, especially when you're going for that nice channel matching between left and right. And so while the process was shown in all of its steps, usually those steps are just multiplied by a lot. It could take several minutes, depending on your level of OCD, to get that thing nailed down. But that is the process that we recommend to mount products, headphones in particular, onto the head and torso. And if you look at the screenshots here from the video, you can see that in this case, left channel looks pretty good. Right channel, across the board, there's a little bit of a drop. This is something that you would correct. You'd go and fiddle with the right ear and the product that's in or on the right ear to make sure that we get something that looks a little bit like that. And frankly, even here, I would argue that sub about 1K 500 hertz, there's still a dB or 2 difference between left and right. I would like to tidy that up, but that's one of the things that you can just do and work on manually for now, but using the online level in Aqua makes it a lot easier. So to sum things up, the messages that we wanted to share with you here was, we wanted to be forthcoming about what this new product line, what this new standard actually means for you. And so we grabbed the 3 head and torso models, the 3 variations that are typically used for telecommunication purposes, and we took some mobile phones straight off the shelf, commercially available. And I think we confirmed and can reassure people that really no matter which iteration of which version of the head and torso you have, mobile phone measurements are going to look nearly identical and nearly the same. And I think you can have a lot of confidence with that. For headphones, though, and headsets, there are some slight differences. Now we're dealing with obviously different products. Headphones are very different from mobile phones. We talk about different impedances and transducer design and choices and amount of transducers for that matter. And so we are going to see differences. The circumaural and the supraaural headsets, maybe for obvious reasons, there are slightly less differences there. But once we get into the concha and into the ear canal, that's where we're going to see the biggest differences. And that's really where we advocate for the choice of the 4.4 pinna. It's a lot more realistic. It's a lot easier to work with. And it's going to give you the most accurate position and fit. And in general, I think we would make the statement that the 4.4 version of the ear is going to be the most accurate representation of the human auditory system. And for some applications, it's going to make a big difference, like headsets, especially in-ear products. For some applications, the use of the 4.4 doesn't make a big difference, like mobile phone measurements, but it's going to give you almost exactly the same results as with the 3.3. And then the last point we wanted to share was that positioning of devices is incredibly crucial. And for mobile phones, we have the automated positioner. That's been around for a while. That's something that we're very confident and comfortable with. For headsets, though, it's still a manual process, but we do have some tools that can make it easier. And I think the next step is to also allow you to use something like target frequency responses in that online FFT version. So if you're using your product one day and you have to take them out at the end of the day for charging or some other purpose, maybe you're swapping out transducers, I don't know. But as you put those products back into the ear of the head and torso the next day, maybe you want to aim for the same target you had the day before to see if there's any difference in your product with what you have chosen to change to it, or at least get back to where you were before. So that's another thing we're working on. With that, I would like to thank you very much for your attendance today and your interest in the presentation. It was really about sharing what we learned about the new ear, its performance with real-world products, and hopefully that makes you feel a lot more comfortable about the different versions that might be out there in the market. If you have any further questions, please reach out to us at Head Acoustics. I'm sure your local representative would be happy to answer any further questions. Thank you very much.